Good afternoon, students. Today, we will not go to a demonstration of X-ray energy specific spectroscopy because we are with a new detector at this moment. It was just installed some weeks ago, and we were not able to configure everything for remote operation. And then I will show something about this technique, the theory about this technique. For sure, it is my preferred spectroscopic technique. I don't know why there was no anything planned for that. Well, the outline of my presentation is I will talk about the generation of characteristic X-ray photons, the detection of these photons, okay? I will talk about X-ray spectra and images, and I will talk about a little bit about the qualitative information that you can get and the quantitative information, the difficulties that you have and so on, okay? Well, first, generation. As you saw in the presentation of Professor Arenal, when a beam, electron beam strikes the sample, we will have many different types of interactions that will generate different signals. For analytical electron, to do analysis of the material, to do analytical electron microscopy, we can use two kinds of we can use two types of signals and some others, of course. We can do cathodoluminescence and so on, but the principal, the main signals that we can use are the characteristic X-rays and the energy loss electrons, okay? This is the commercial available instruments that you can get for analysis, okay? And then with these signals, we can use for analysis of the materials, all the materials in the TM, and then we will get an analytical electron microscope. The idea is just by having these spectroscopic techniques, we will change the instruments for just imaging, high-resolution imaging and so on, the structural characterization for a chemical, elemental determination of your material, okay? With a lot of spatial resolution also. Well, about the inelastic process that will carry compositional information about your specimen, we have many inelastic process, as are you looking in the other presentations. And here we have a graphic relating the cross-section of for scattering, okay, related with the beam energy. We can see that among the inelastic process that we have this process that generates X-rays. This is the process that we are interested in. We can see here the plasmon scatterings, elastic scatterings, and these two kind of scatterings here that generate L-shell transitions or K-shell transitions. We can think about this graphic related with the probability of the occurrence of this kind of event. And then you can look very easily that we have a lot of a very high probability to have this kind of events. And then it's interesting for us to try to detect these the signals that are generated here, and we will get compositional elemental information about our specimen, okay? This is one X-ray spectrum, okay? that was acquired in by a specific kind of detector, the energy dispersive spectrometer. We will see something in some moments, okay, about it. Well, here we are. Here is the spectrum. This is from pure platinum that was acquired at 100 kilo electron volts. Okay, we can see here two types of X-rays that are formed by the interaction of the electron beam with the matter, with the material. Okay, we have the continuum X-rays, the brainstorm, we call it brainstorm X-rays, that forms the background in the spectrum. Which background? Background is related with this noise that is superimposed with the peaks of the elements. Okay? Well, we have this noise, the brainstorm, and the peaks, the characteristic X-ray peaks. That depends on the type of elements that you have in your specimen. Here we have pure platinum, and then we can see we have the platinum M signal here, platinum L, and so on, and all many different peaks of these same elements that we'll see in some slides, the difference between them. But this is the idea. We have the peaks and the background, okay? If you have some question, please just stop me and we can go for the resolution. I need to go very fast because of the time, okay? Well, talking about the brainstorm, this background that always is formed in an acquisition of EDS spectrum, the situation you get is that the incident electron will go through the material, through the electron clouds of the material, and there will be a coulombic interaction between the electrons of the material and the incident electron. This will cause a force, a stopping force in the electron that is going through the material. And this interaction, if these incident electrons do not hit, do not shock with any electron, specific electron in some cloud, but just passing through the orbitals, it will feel a braking force, okay, a coulombic force, and it will generate X-ray photons, okay? This is the idea. It will generate X-ray photons that will come from the maximum energy, the zero, the E0, the energy of the beam, okay, to zero, okay? It's very, very not probable that an electron will lose all its energy in this braking force, okay? Then there is a probability distribution of the brainstorm. Brainstorm, you have this shape here, the generated brainstorm will always have this shape, okay? Because the very small losses are more probable than to lose all the energy, okay? And this is the situation that we have. During the passing of the electron through the material, many X-ray photons are generated, okay? This brainstorm is highly anisotropic, okay? It shows a strong forward scattering, okay? It's always forward scattered. It means that you have your material here, the incident beam is coming from this side, and then all the brainstorm will be formed in the other side of your material. Okay? Let me see if I have something more. Well, you always have this. we will see something about this difference here, generated and detected. It is related with the detector, some specificities of the detector. For the generation of the X-ray photon, we have the same as we have in the same as we have in EOS. The event that generates an EOS, an energy loss electron, okay, is the same event that generates an X-ray. Okay, this is very important to keep in your mind. Then we have a critical ionization energy. Okay, the beam needs to transfer some energy that is greater than the value for some transition, okay, to ionize the electron in your material, okay. And the critical ionization, this critical amount of energy, the critical ionization energy, is what we measure in the energy loss spectrum, okay? But in the case of the EDS, in the case of the EDS acquisition, we use the same, exactly the same event, okay? But we will not measure this electron that lost some energy, okay? But we will measure an indirect event that is the relaxation of the ionized atom. Let me describe this diagram first, please. Here you have the energy levels of your atom in the sample, okay? Here you have the incoming electron from the electron beam. It's schematic for sure. And then there is this incoming electron will will hit a K level electron and will ionize the material, okay? Then the electron will go to the continuous states above the Fermi level, no problem. And then what we will have is that this difference, the electron now is ionized. Then an outer shell electron, in this case here, the L3 electron, will come to the K shell to replace this electron that was ionized, okay? And this energy difference between L3 and K will be released as an X-ray photon or an OG electron, with, depending on the fluorescence yield of the element and of the event, of the group of energy levels that are involved. Okay? It's clear how we generate the X-ray photons. We just hit the electron of an internal shell electron. It will be ionized, and then the atom will decay to replace to stabilize this ionization, and will emit photons, X-ray photons that are element specific. All the elements will have specific amounts of energy that are related with these specific transitions. Okay? Here we have another graphic with a fluorescence yield and the dependence of the fluorescence yield with the atomic number of your material. Okay? We can see here that the generation of the X-ray photons is higher when you have a higher atomic number, Z atomic number elements. As Professor Raul said, there is it's complementary. Both techniques, EOS and X-rays, they are complementary techniques. With EOS, you get more easily, to say, light elements. You can analyze it more easily. And the X-rays, with the X-ray spectrometry, you can have information in higher atomic number elements. And it's a very good idea to use both techniques complementarily, okay? And it's clear this idea of the probability. This is very important for all the spectroscopic techniques. There is always a chance that you have the information, okay? And you need to deal with it when you when you perform an experiment, okay? You need to know about the probability of the generation of your element, okay? Well, let's continue here. It's very interesting to compare here the critical energy for ionization of an element and the characteristic X-ray that it's generated. It's easy to see that the critical ionization energy is always higher than the energy of the characteristic X-ray. This is why we have, for the relaxation of the ionized atom, we have the cascade to the ground, okay? The atom will, you return to the ground state, not via a single event, but a cascade of transitions that will depend on the complexity of the electronic structure, okay? It's clear. We have here, for instance, the silver. We have this difference about 3 kiloelectron volts, but for carbon it's very close, because carbon is very simple. You just have the transition and then some few steps to go to the ground state again. It's clear this? Okay? May I continue, please, if you have some question? Here, just to illustrate, we have all the possible electron shells that are involved, okay? We have here, for a K transition, we have K alpha, K alpha 2, K beta 1, beta 3, beta 2, all these possible ways to relax. What you need to think? I ionized this K electron from my element in my material, okay? Then it will be ionized. There will be all these possibilities here of decaying of the element, of the atom, to the ground state again. And then I may have K alpha 1 amount of energy. I may have a K alpha 2 amount of energy, K beta 1 amount of energy, and so on. There are many possibilities of decaying. What it means? It means that we have between one single event of ionization, we may have probabilities, we call it weights, okay, of having one specific energy or other. It means that the element in the material decayed by one step, one way or another way. it's clear? Let's see here. Family group, blah, blah, blah. We have, in all these, we have all the X-ray lines. Let's call by the correct number, name. X-ray lines, they are the K line, L line, or M line. This is the first thing to be in your head. Then we have the families. The families are the, when you are measuring, this is important to understand. When you are measuring, you will measure 100, you measure for the K line, you measure K alpha and K beta, okay? If you got the proportion of all the photons that you measured, you have a proportion of 10% of K beta and 100% of K alpha, okay? You always get this proportion, okay? Then you see that there is a probability of decaying following one way or another way. And then have a look again. Here is the alpha. It is grouped alpha 1 and alpha 2 in the same K alpha, okay? The difference in energy is very, very small. And here you have the possibility of K beta. And then if you have an event that you measured K alpha, it came from an L shell electron decaying. And the other is from the M shell and so on. Okay? It's clear? I'll continue. Then we have the detection of these characteristics. Then we have in our mind now that we have a probability for the generation of the X-ray photon. We have probability of decaying of your element following different steps, and you measure differences in energy also, okay? Well, for the generation of X-ray photons, you ionize your atom. The atom, the electron will deviate the electron from the beam by a very, very small angle, okay? And then if you collect this electron that you can keep the resolution in space, because it was very deviating in a very small angle, you have all the possibilities of EOS, okay? EOS spectroscopy you get with this electron. And by going to the ground state again of this element, we will have the generation of the X-ray photons, and the resultant characteristic X-ray will be generated as a spherical wave emitted uniformly over 4p stereo radians. Okay? It means what? It means that we will have from the point where you are being strike your sample, it will be a spherical wave, okay? All these photons will be emitted through space, okay? With this shape of a sphere around the point of incidence. This is the idea, okay? And then we start to have some problems. This is why people like to compare EOS with EDS, because EDS is too much problematic in measuring the signal. For the EOS, we have a very simple situation, because we have here your beam hitting the specimen and the electrons that are deviated by a small angle going through the column, following the optical axis. It's just to continue there and acquire, to put an aperture there and collect all the signal that you want, okay? And then for use, we have, in this solid angle of use, if you collect, if you put your spectrometer just in the optical axis, you will get most of the electrons that that had lost some energy, okay? But for the X-ray collection, we have a different situation. We have all the X-rays being emitted to all these angles, and we need to choose a specific place to collect it, to put your spectrometer and collect it. You had lectures on the instrument last week. Then you know that the space inside the pole piece of the microscope is very, very limited. We have many instrumentations on the lenses, and your sample is inserted in a very, very thin space, small space, okay? And then your you have your sample there, and the X-rays are generated spherically from your specimen. And then you need to put a spectrometer there. It's a very complicated task, okay? It's a very complicated situation. And then there are many different designs. I will show something about it. But the collection of these X-ray photons is very, very problematic related with this situation, the way that it is generated, okay? And then you can see here, just for comparison, this EDX spectrum, you have thousands of counts of one element, but in the EOS spectrum, you have 10 elevated to 10 and so on, so much more counts for the same element, okay? Well, here I show the interface between the EDX spectrum, spectrometer and the TM, okay? You can see here the specimen, it's a specimen with a hole inside it. It's that kind of specimen that I showed the preparation where you make a dimple inside of it, and then you excavate a small hole in the center. Then usually people tilt the specimen in the direction of the detector to improve the collection of the electrons, okay? And then this is the situation. The incident beam is coming to the optical axis. You have your specimen, you have your pole piece, and here to show is the continuum that is generated, the brainstorm electrons, okay, sorry, brainstorm photons, okay, and all the characteristic photons are generated here spherically for all these parts, okay, but you just collect it here, very small piece inside your microscope. Well, here is what look like the energy dispersive spectrometer. This is an old one. It's a the conventional SILI detector. Is the silicon lithium detector. It is how can I say? Now we can say it's an old-fashioned spectrometer because now we have an SDD, a brand new SDD. This is why I'm not making it a demonstration, okay? This is the old detectors. We have a very, very big dewar for liquid nitrogen because it works in here is the cold finger that comes to the crystal that is the actual detector of this EDS. And for this detector to operate, it needs to be operated at liquid nitrogen temperatures. Okay, the present detector we do not need that. Okay, well, we have these typical detectors, this silicium lithium. This is the most famous one, but now it's being more and more replaced by this silicon drift detector, the SDD. This intrinsic germanium, it's not quite common, okay? The idea is the incident X-ray photon, okay, will hit the window here of your detector and will create electron-hole pairs inside the detector, and will lose all its energy until it is completely absorbed inside the detector, okay? This will create an amount of electron and hole pairs, and this number of electron hole pairs is proportional to the X-ray energy that that entered inside the detector. The idea is the silicium detector is a reverse biased PEN diode. Okay, you have here a difference in potential. Okay, about 1,000 volts, and then the X-ray will deposit the energy, all its energy, when coming inside the intrinsic active silicon part of the detector. It will lose all its energy and will transfer its energy. Sorry, this X-ray will deposit energy, and the electrons are transferred from the valence band to the conduction band in the silicon inside the detector, okay, and will create these electron hole pairs. A single event of this transition, okay, amounts 3.8 electron volts. And then for the creation of something like this energy, the nickel K alpha peak of the in the energy dispersive spectrum, what we will need, it's about 2,000 transitions to be measured, to be transferred for the spectrum. Is it clear? This is not clear. Let's see. One event, when the photon arrives in the detector, it will create electron hole pairs. Each one will, in each one of these events, it will lose 3.8 electron volts. It will need to use all its energy, okay, until it finishes its energy. And then you have an amount of electrons that will be, because of this difference in potential, will be measured here as a current, okay? This amount of current will be translated in voltage by the electronics of the system, okay? And then this amount, this voltage will be identified to some specific energy of the incoming X-ray. It's okay? It's very simple. Well, let's continue here. these conventional detectors, we used to have window a window in front of the detector, okay, to protect the system. This is the idea, okay. And then in former times we had different types of windows to be used, and all these windows will have some impact in the measured spectrum, okay? What we have, when an X-ray arrives here and hits the window, and the gold, there is also a gold layer in front of the detector for the connection here, okay, of the potential difference, okay. When the photon comes here, arrives here, what we will have is that these small energy photons will be absorbed by this window or this gold layer in front of the detector, okay. This is why we have this problem with the light elements for the use of the EDX spectrometry for detecting these light elements, because of the small energy of these photons, they may be absorbed. And then if you get here thinking about probability again, okay, you see that the probability of the detection using different kinds of windows, you see that always is very poor here for low energy, okay? And then we come to the next step, that is to be windowless, okay? Then it's the best possible performance to be windowless, but even in the windowless detector, you have problems in passing through the gold layer and so on for the detection, okay? You can see here, this is a ultra-thin window compared with a windowless detector. You can see here the proportion of the small peaks. It's, you can see more counts for the windowless related with the ultra-thin window, okay? Okay. Then we go to resolution of the EDS, this kind of spectrometer. Well, see, we are dealing with the X-ray energy dispersive spectrometers. This kind of spectrometer that I showed, it's called energy dispersive spectrometer, okay? We have a dependence about the resolution of the detector and the amount of signal that is being processed by the spectrometer, because you saw that we have a parallel detector that get photons that arrives to the detector with different energies, okay? And this detector measure all these different energies at the same time, okay? It's different from a prism, where you select a specific energy to be measured each time. Here not. All the photons that arrive with different energies are being measured at the same time. But you saw the photon arrives to the detector, it needs to have some time, some finite amount of time to lose all its energy, to be measured by the detector, and then the detector will say, oh, I got a photon with that energy, and then the detector will start again to measure. You see? because you may have many photons coming, and all these events will create an amount of electrons, a small current that will be measured as a photon. Okay, if you make the incidence of the photons, if you, how can I say, if many photons at the same time arrives to the detector will not deal with all these photons, will not have time to deal with all these photons, and then you can choose some parameters in your detector. One is the process time. Okay, it's more important. Is the process time. Is the time the instrument will be off, the detector will be off to measure just one event. Okay? And then we start to think about the dead time of the detector. Okay? Because the detector will need to be off for some time to perform its work. Okay? If you are put too much, too much photons, but by how do you put too much photons? You put too much electrons in a very bulky part of your sample. It will generate a lot of many photons, and then it may saturate your detector. Okay, and make the dead time too high, okay? Or you can work in a situation with a smaller dead time to make your detector to work in a correct way. Why I'm talking about the dead time? Because with a large dead time, I will start to have loss of resolution in my in this experiment, the detection of the X-rays. Because if your detector is not being able to deal with many photons, it will start to have all the different kinds of, how can I say, artifacts that come off these type of detectors, okay? You need to work in a very stable way to have the best possible resolution of this kind of detector. For these, the energy dispersive spectrometers, this number 140 eV for the manganese K alpha, okay, it's a standard resolution for this kind of spectrometer. That's very different from use. Use, you get 1 eV of resolution or less. It's really different. You have information with use about the environment where your atom is. Okay? Here in EDS, you just see that I have this atom. Okay? I can see that I have this atom. In use, no. In use, you have information about the environment, chemical environment, and everything that Raul is showing you. Okay? Well, this is the new detectors that is similar that that we have here now. It's a SDD detector. The difference is not, I don't have anymore a cylindrical detector where the photon arrives from one side and it's measured for the other side. But now I have a small plate with many rings where we put different voltages, different potentials, okay, in these rings. This is the part where the X-rays arrive, and then the other side of the detector, I will have these rings, these conductive rings, where I put some potential, negative potential. Then what we will have? When one photon arrives here, it will start to lose energy and generate electrons and holes, okay? All these electrons will be, will have a repulsion, electrostatic repulsion with these rings that are in the other face of the detector. And in the very center of your detector, you have an anode that is linked with this system that will actually measure the amount, the current that is being generated, okay? And then now I have not a cylinder that one photon arrives here and is measured there, okay? But I have a small plate where many photons come, and all the electrons are being generated, and they are directed to the center of the detector, okay? And then you have the possibility to have photons arriving in different positions of your detector, and all of them, this is the timeline, okay? This is the signal of the charge collection, and you can have many different events in a smaller amount of time, okay? Two photons may arrive at the same time, and they may be measured by the detector. You just need to have a small amount of time where there is no change in the current, the measured current, to the detector be able to separate both signals. Okay? Here is how it looks like. Okay, you don't need any more of liquid nitrogen temperatures. You can work with Peltier cooling. Okay, and we have this shape. It's not circular, actually circular. The new detectors, they have this teardrop shape, where the anode is here, that it's isolated from the place where the photons arrive. Then it optimizes the detection of the electrons, of the photons, by do not include the difference potential that you have here in the anode. Okay? Here, about the SDD again, you have the control of the process time, like I said. Here is a comparison. You have a key here. The process time here, the peaking time, okay? And the SDD, you have a very, very pretty larger resolution with very, very small peaking times that when you compare with the silicium-lithium conventional detectors, okay? You have a pretty better detector. This is the idea. Here about the interface again, the angles that we need to think about when installing an SDS detector are the collection angle, okay? The collection angle, that means it's measured in stereo radians, okay? The complete sphere is 4p stereo radians, okay? That it's about 12, 13 stereo radians, okay? In the commercial instruments, we get you can acquire 0.1 or 0.3 stereo-radians. And then you can have an idea of the amount of signal that you are throwing away during an experiment, okay? But it's, I think it's clear for you that why you have this problem. It's okay, it's clear? Please? Okay. Well, the conventional detectors, we had these 0.3s, the best we can. Now, with our new SDD detector, we have about this 0.3 stereo-radian in our FAG machine. And we are very, very excited with our new machine, the double-corrected Titan, where we have an EDS spectrometer with 4 detectors that are symmetrically arranged around the sample. And then this idea to tilt the sample to have more or less signals completely not useful anymore. And I guess for this machine, it's 0.9 stereo-radians. That it's really a lot of signal being collected. Another important parameter is the takeoff angle. That means the angle between the front face of your detector and the optical axis of the microscope in the surface of your specimen, okay? Typically, it is between 20 and 70 degrees, okay? Well, related with these conventional detectors where you have conventional microscopes, where you have just one detector attached to the column, we have these problems here related with the relative position of your specimen and your detector. If you have your detector here, you can imagine which kind of sample you have here. Remember about the dimple prepared sample. You have a dimple in the center, and then you just create a hole inside it with the electron ion milling system, and then you have the electron transparent really in the border of this hole. And then the appearance of such a sample will be something like this, okay? A very, very thin place here, but thicker regions in the direction of the edges of your disk, okay? If you strike your beam in this position and this sample is oriented against your detector, you have all this distance to be traveled by the X-ray inside your sample before to be detected in the detector. But if you position your sample looking for the detector, you have a smaller path inside your sample to be detected. Then this kind of geometrical positioning, it's important when you are dealing with EDX measurements. Okay, the same here. This starts to be a very complicated situation when you have here an interface, and depending on the geometry of your sample related to the detector, you may detect or not some signals. Okay. There are some artifacts. I will go very quickly here. We have the possibility to have escape peaks. Why escape peaks? If you have many, many, many photons of one energy, it will be probable, the probability of one photon arriving in your detector, instead of creating an electron-hole pair, it will fluoresce silicon inside the detector, okay? And then it will lose the energy, the amount of energy of the silicon. And then you start to have what we call escape peak. That is the energy of your element minus the energy of the silicon. But it's caused by the detector. If related with this also, if you count a lot, you always, there is no need to count too much. You always have silicon. But it's not silicon in your, it may be in your sample, but you always measure silicon from your detector, okay? From these stray electrons that may fluoresce one silicon, okay? Another conventional artifact is the sun peak. You have here many counts of one element, and you start, with you count really long, you start to have the sun peak. It's the double the energy of your principal element. This is why the detector was not able, the electronics was not able to differentiate two photons arriving at the same time in the detector. Okay? Another, then there are many problems related with the generation of artifacts. You have pre-specimen effects. In your system, if you do not hit anything, you just pass your beam through the vacuum without hitting your sample, and you detect EDS, you always will measure signal, okay? You measure signal from copper, you get signal from chromium, iron. They are all from the instrument, okay? This is what we call the whole counts, okay? The whole count. There are this spurious radiation, okay, that will always be measured in all the microscopes that we have, because of these interactions, okay, of the electrons, the stray electrons that hit your column and generate these X-rays. And these X-rays will come through your column to the detector, okay? And there are also these spurious X-rays, okay? That are those that come from the specimen, but are not generated by the electron, okay? By the electron probe, but are generated by these X-rays that come through the column, okay? And then it's very interesting because these stray X-rays that come through the column, you always get a different kind of, a different proportion in your peaks. You remember that the K, the L transition was more probable than the K ionization. I show it just to remember you, okay? The K is more, sorry, the L is more probable than K, okay? But in this situation here, when you have just an artifact, this is not real, this is an artifact, okay? You have this kind of inversion in the signal that you measure, okay? This is why it's not real, because all the low energy X-rays will be preferentially absorbed in the way to the detector. the higher energy will lose less intensity, and then the proportion will change. Okay? But this is artifacts. Here, the post-specimen artifacts that you may have. Well, you have here the brainstorm, and you may have some electrons that hit parts inside your microscope and then generate X-rays. It may strike here and come through your specimen. You are analyzing this region, and there is a signal that's measured far from the place where you are irradiating your beam, and so on. Well, EDX is very, very problematic. You have many problems with the artifacts, with spurious signals, and so on. But as I said, it's my preferred technique. It's very simple to be used, okay? It's very reliable. All these artifacts, they were well described. Well, when you know everything this, you can use the best of the technique. It's very simple, and our pretty new microscope, double corrected, have 4 spectrometers, and then it's okay. We can live with this because we know about it, okay? Here, they say that copper is everywhere because copper is a conventional element to be inside the column, okay? I will go very fast. Here's the types of analysis that you can do. You can do point analysis. It's really, really important. You solve many important problems of your material by dealing with these. You just focus your probe. You don't need to be in STEM mode. You can do simply in the conventional TM. I would like to see this particle. You just go there, focus your beam on your particle. All the signal will come from that particle. For sure, with all the artifacts involved, okay, because if you are focusing, you have many stray electrons, blah, 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 but the information comes from there, okay? You can be sure about it. It's very important. And then it's very easy to do. It's very useful. You have the possibility to do line scans. With line scans, you can follow difference across the object. You can see around the object which difference you have. And for those who have stable machines, state-of-the-art instruments, the best analytical technique is spectrum imaging, okay? But if you talk with people of the old generations, perhaps they will say that no, the spectrum, to do mapping is to lose time because you are not precise and so on. But this is something related with the old machines, the old way of principally related with instrumentation, with the old instruments. With the new instruments, they are very reliable, very stable. You can do mapping with a lot of, not that easy, but it's easy, okay? And then you can acquire all the information in a single experiment. It's very, very interesting to do, okay? And then, well, with this you do everything. Well, for related with the probe that you are using, because you want to do the best image, and again, and in parallel, you want to do the best spectroscopy also, okay? Thinking about the corrected instruments, just the numbers, okay? For a good ADF STEM imaging, you want to have 30 picoamps or less. For EOS, 100 picoamps. And the XDX analysis, you put all that you can, okay? Because even with the best machines, the best spectrometers, all the best, the technique is not good. You have many problems, you need to deal with many limitations, and then you need to put all the signal you can in your sample, okay? Then there is this compromise between the image you get, the resolution of the image, and the spectroscopic information you can leverage from this pyramid. Here, about the spectrum imaging, as Professor House showed, by doing spectrum imaging, what you do, you focus your beam in the STEM mode, okay, scanning mode. You will acquire one single spectrum in each pixel of your image. You choose the size of your image, let's say 20 by 20 pixels. In our instrument, it's conventional to use 24 by 24. And then you stop your beam for a specific amount of time in each pixel, and in each pixel it will acquire a complete spectrum, okay? Use spectrum or EDS and so on, okay? And then it will go to another pixel in a delay time, and then going, until it acquires the complete surface where you choose the experiment. And then, by the acquisition of this, you arrive with the data cube, okay? The data cube is something like your image, but with all the spectroscopic information in Z, okay? And then if you, with this, you can do post-acquisition processing. You have the data cube, and then you just go there and get some layers of your cube that will be related with what? With the peaks. The XDX peaks. Okay, if you put your spectrum here, I want to get this peak. You just go in this specific energy and acquire this layer. And then you have the distribution of photons in the space you got related with that specific energy, okay? Here, there are some easy, examples, okay, of comparison of EOS and XDX. You can see here from the scale bars that the experiment is, the information, it's about the same quality. You have, with the aberration correction microscope, all the kind of spectroscopy you can get with an incredibly good resolution, okay? Here it's a very interesting example of one of my samples. It's a gold palladium material with separated phases. Here you have the particles in bright field and EDS. And if you go for the mapping, EDS mapping, here is the palladium L signal. Here is the gold L signal. This is the gold M signal, okay? I am interested in the same shell of the elements, because then there are the same probability of generation of the photons and so on. Then the comparison is more reliable, okay? And then what we can see here is this region that was mapped. We can see the ADF, you see that it's a Z contrast technique. You can see clearly here that the brighter particles are made of gold, okay? And the darker particles are all made of palladium, okay? But now you have compositional information about this system, okay? Well, here about the spatial resolution that we may have, okay, the smallest distance between two volumes where we can have independent analysis, okay? The one of definitions that we see in the literature is this. The radius, the resolution is considered the ratio between the diameter of your beam in the entrance of your sample and the exit of your sample. Okay, this is a way to define resolution for this spectroscopy. This is a way to measure experimentally the resolution. Is just by to acquiring in a line scan, for example, you have here an interface in your material, a very defined interface. When you come scanning the beam, you will start to measure the composition of the one element, okay? And then when your beam, the cone that it's formed by the scattering, when it passes through the interface, then you have it, you have 100% of the other elements. And then by measuring this distance here from 2% and 98% of the intensity, total intensity that is measured, when you multiply by 1.414, then you have one experimental estimation of your resolution, okay? Well, now I will go very fast for the last part here of comparing qualitative and quantitative analysis in XDX. It's very important to do qualitative analysis because you don't lose time when you go for quantification. But as I told you, it's very important to know a lot about your experiment before to go to analytical electron microscopy. TM should be the last technique to be used in a non-foil or even in a work, in a project you are working on. TM, the best TM, the analytical electron microscopy and so on, all the description of your material will just make sense with more information about the population of your material, more general information, because TM is very local. You may be describing an artifact of your material, okay? Well, for quantitative analysis, you can do, use the auto ID of the software of acquisition. There are possibilities to use, there are some slide tools where you find the families of your elements in a slide. And you can do the manual identification using the standard, the characteristic values of energies of each element. You just come with your spectrum and check for the individual lines and the families. If all are there, then you can identify for sure a specific element, okay? Then you can see here, when you go to the, here I have the antimonium L line. You can see that there are many different signals coming from the different families. You need to find it. If it's not, then it may be another element, it may be an artifact, and so on. Okay? When you have your system, you just need to look for all the possible combinations. Okay? Well, semi-quantitative analysis in AM, it's very easy, okay? To a first approximation, the height of the peaks may be used to be proportional to the compositional, the elemental composition of your sample. It's a very approximation. It's very crude approximation, but it runs pretty well. Okay, because the EDS, you always have a large uncertainty in the determination of your quantitative results, and just by measuring the height of the peak and comparing the peaks, you have a good approximation of your composition. Then you can run in this way. This is why, please take attention, this is why we are dealing with the thin film approximation. What is this? We are with a we are in the TM, with a TM sample that are about 100 nanometers in thickness or less, okay? Then the effects that you have of X-rays related with fluorescence or absorption may be ignored. You just have the influence of the atomic number generating the characteristic signals. You don't need to take care about absorption and fluorescence. Then this is why you can do it very easily. Don't do it in the SEM sample, please. You always need to have a thin specimen. For the thin specimen, you have what is called the Cliff-Lorimer ratio technique, okay? With this technique, it's very simple. You have here the weight fraction of your element, okay? It is equal to the K, what is called the K factor, and multiplied by a proportion between the number of X-rays, the intensity of X-rays measured for each element, okay? You just integrate your peak and use for this kind of proportionality, okay? It's not that easy because it's easy as this, okay? But if you go for quantification, you start to think in the precision of your quantification, then start to have many problems, First one, which X-ray line should I use? I have these problems here of the detector that will not get the information of these low energy elements. We will lose actual information. And you have also here, here is the fraction absorbed by the detector related with the energy. You see that the silicium-lithium and the SDD runs in a similar way. You have all the X-rays absorbed being measured just in a very small region here that comes from about 2 or 3 kilo EV to 20 EV, okay? And then you can deal with this information just in this region of energy, okay? And we have also here the probabilities of the generation of the photons and so on. Background subtraction. You need to deal with the background for quantification. And just putting problems for quantification. Semi-quantification, where you are not interested with exact value, it's okay, it's very easy. But quantification, we need to deal with all these problems. How to subtract the background, Here are the simple ways to do it. It's just to get a window before, one after, and subtract from the integral of your peak and so on. It's important to use the full width half maximum of your peak because it's a spectroscopic signal. This is the best way to measure it. Okay. Actually, they think that's better to use a slightly higher window to measure it, and I used to do it also. And then we arrive to the problem of K-factor calculation or determination. There are many ways to do it by first principles, but we arrive in difficulties because we don't know exactly all these parameters. And what we get with the softwares is that they are black boxes. They calculate everything for you, okay? But you don't know what they are doing with your information, okay? Then it starts to be too easy. I need to stop now because we are running in troubles with time, but I almost finished it. I just show some quantification. XDX is a mature and well-established technique. It's very good, much easier than EOS. We will have a very best machine here. It's the technique to be used in the future, the near future. Thank you.